This video is a tutorial on the combustion analysis version of determining an empirical formula. If you'd like a basic introduction, go back and look at my empirical formulas video. Empirical molecular formulas for compounds that contain carbon and hydrogen, or carbon, hydrogen, and oxygen can be determined with a process called combustion analysis. The steps for that are: you're going to weigh the sample of the compound to be analyzed and place it in the apparatus. You're going to burn that sample completely with the products of combustion of a compound that contains only carbon and hydrogen, or carbon, hydrogen, oxygen, or simply carbon dioxide and water. The water and carbon dioxide are drawn through two tubes. One tube contains a substance that absorbs water, and the other contains a substance that absorbs carbon dioxide. You weigh each of these tubes before and after the combustion. The increase in mass of the first tube will be the mass of the water that was formed in the combustion, and the increase in mass for the second tube will be the increase in mass will be the CO2 formed. Assume that all the carbon in the compound has been converted to CO2 and trapped in the tube. Then you calculate the mass of the carbon in the compound from the mass of the carbon measured from the mass of the carbon dioxide formed. You can similarly assume that all the hydrogen in the compound has been converted to water and trapped in the first tube, and then calculate the mass of the hydrogen in the compound from the mass of the hydrogen measured from the mass of water. If the compound also contains oxygen, you want to calculate the mass of the oxygen by subtracting the mass of the carbon and the mass of the hydrogen from the total mass of the original compound. We can then use this data in the very same ways as we did in the previous empirical formula video to determine empirical and molecular formulas. This is the basic setup. We're going to put a sample in our furnace. We're going to, of course, heat that up and burn it. We're going to collect the water in the water tube and that absorbent material, and the CO2 we're going to collect in the CO2 absorbent material. We're going to inlet in excess oxygen to ensure a complete combustion. Here we have a 0.425 gram sample of propene, which contains only carbon and hydrogen in this case. Burning it produces 1.336 grams of carbon dioxide and 0.546 grams of water. We want to know the empirical formula of propene. So we got 1.336 grams of carbon dioxide divided through by 44.01 grams of carbon dioxide per 1 mole. There's 1 mole of carbon dioxide to 1 mole of carbon. Crank that out, we get 0.0304 moles of carbon. Similarly, for the water, we take 0.546 grams of water, divide through by 18.02 grams of water per 1 mole. But there are 2 moles of hydrogen for every 1 water. Make sure we include that ratio. We get 0.0606 moles of hydrogen. We can use the moles of each of those to calculate the empirical formula. We can see the moles of carbon is less than the moles of hydrogen, so we'll divide both of those through by the moles of carbon. 0.0304 moles of carbon divided by 0.0304 moles equals 1. Moles of hydrogen, 0.0606 moles of hydrogen divided by 0.0304 is about 2. So we can see the empirical formula of propene is CH2. Here is a slightly more complex problem where we have 0.255 gram sample of isopropyl alcohol, which contains carbon, hydrogen, and oxygen. Burning it produces 0.561 grams of carbon dioxide and 0.306 grams of water. We want to again know the empirical formula. So we take the 0.561 grams of carbon dioxide. We're going to divide through by 44.01 grams of carbon dioxide per 1 mole. 1 mole of carbon dioxide to 1 mole of carbon. We're going to get 0.0127 moles of carbon, just like in the previous example. However, I also need to get an oxygen somehow, so I'm going to go ahead and calculate the grams of carbon as well. Times 12.01 grams of carbon per 1 mole, give me 0.153 grams of carbon. The only reason I calculate the grams is to get at the oxygen. The moles are what I need to calculate the empirical formula at the end. We'll do the same deal for hydrogen from water. So 0.306 grams of water divided by 18.02 grams per 1 mole of water. 2 moles of hydrogen, 1 mole of water. We're going to get 0.0340 moles of hydrogen. Again, I need grams to get at oxygen. So times 1.01 grams of hydrogen per 1 mole, we get 0.0343 grams of hydrogen. Subtract both those masses calculated from the original sample. So 0.255 grams of sample minus 0.153 grams of carbon minus 0.0343 grams of hydrogen, we get 0.068 grams of oxygen. Now, if I get the moles of oxygen, then I can calculate the empirical formula. So 0.068 grams of oxygen divided by 16 grams of oxygen per 1 mole gives me 0.0042 moles of oxygen. That being the smallest of the 3 moles formed, we'll divide them all through by 0.0042 moles. So 0.0127 moles of carbon divided by 0.0042 moles is about 3. 0.0340 moles of hydrogen divided by 0.0042 moles is about 8. And then 0.0042 moles divided by itself is, of course, 1. Yielding an empirical formula for isopropyl alcohol of C3H8O. This has been a brief tutorial on combustion analysis as it relates to empirical formulas.